Welcome to the online lecture series on power electronics. These days we are discussing DC-DC converters. In our last lecture we discussed about buck converter, and today our topic of discussion is boost converter. A boost converter is commonly known as step-up DC-DC converter, which means that at output we will be getting a higher level of DC voltage as compared to the input voltage. Whereas in case of buck converter, the output voltage obtained was at a lower level as compared to the input voltage. Therefore, it is needed when we require high voltage at output as compared to the source voltage. The basic element of a boost converter are an inductor in series with this supply, a diode and a switch. This configuration of inductor, diode and switch makes up the boost converter. Just like the buck converter, the boost converter also has two modes of operation. In the first mode, when the switch is turned on, and the diagram for that is shown over here. During this first mode, the current flows through the inductor and switch, and in the second mode, when this switch will be in open condition, in that case this will be our circuit, and we will have an inductor diode in series, and the path of current will be this. From inductor to diode towards the load and then back to source. Now the equation for the charging time of the inductor can be written as EMF produced across this inductor is equal to L delta I by delta T. So this voltage is equal to the source voltage. Source voltage will appear directly across this inductor. Vs is equal to L delta IL over KTS, because this is during the on time and the switch is on from 0 to KTS. TS is basically the total time period and K is the percentage of time for which this switch will be on, and the end result is delta IL is equal to KVS over FL. Okay, when the switch is open during the second mode, we know that the inductor will be discharging. Therefore, the voltage across this inductor can be governed by this basic equation VL is equal to L delta IL over delta T, and the voltage across this inductor during this off time is Vs minus V naught. L delta IL over 1 minus K into T. Instead of delta T we have used this time, that is the off time. If the switch is on for KT time, so the switch will be on for 1 minus K into T. Delta IL can be found from the above expression by simple cross multiplication and rearranging this expression. So delta IL during the off time of this switch is equal to 1 minus K into Vs minus V naught over FL. Okay, so for steady state of operation, the net change in inductor must be 0. The sum of the current delta IL, the change in current from the inductor during the on time, and the change of current in this inductor during the off time must be 0. This is the current during the on time, and this is the current change during the off time. So FL and FL was common in both of these, that when shifted to the right side cross multiplied becomes 0, or you can say that FL has been eliminated from this equation. KVS plus 1 minus K Vs minus V naught is equal to 0. KVS plus this term multiplied by this Vs minus V naught minus KVS plus KV naught is equal to 0. This expression, in this expression, KVS and minus KVS will be eliminated. So we are left with Vs, V naught and KV naught. Therefore, writing them over here, Vs minus V naught plus KV naught is equal to 0, and keeping the similar terms on one side, Vs is equal to V naught minus KV naught, which implies that Vs is equal to V naught times 1 minus K. And finally, the output voltage V naught is equal to Vs over 1 minus K, where K is the duty cycle and it can be varied from 0 to 1, that is from 0% to 100%. Therefore, since the K is in between 0 to 1, therefore this 1 minus K term should also be less than 1 and their reciprocal will be greater than 1. Therefore, V naught will always be greater than Vs. The output voltage for a boost converter will be greater than input voltage.